Hello. All right, it's been a long time since we wanted to do this episode. Um, I was somehow reluctant to talk about consistent hashing. Don't really know why, to be honest. It always felt like a topic that is not necessarily closely tied to system design, in the sense that the true complexity of this is in the algorithm, in the implementation, whereas the system design part is mostly explaining why is it a good idea. Eventually I gave in. We had an off-the-record episode when we spoke for well over an hour about consistent hashing. I'm fully convinced it's a worthy episode. Let's give it a shot. Public service announcement. A lot of people already congratulated me. It's approximately mid last week. The meetup was 1 year old. So thanks for being here. Way to go. Consistent hashing. Basically, it's important to distinguish between two aspects of consistent hashing. On the one hand, it's a useful system design concept. On the other hand, it's a really neat algorithmic implementation that makes certain things possible. My view is that it's essential to understand both individually and in combination. Because so I sometimes talk to people about their interview experience, and it's considered to be an advanced topic, consistent hashing per se. So when people think they know it, I tend to ask about that. Interviewers tend to ask about that. And far too often, people just talking about the implementation, this ring thingy right away, which I don't think is not necessarily wrong, but I think it sends the wrong message. I think it's a storytelling mistake to start talking about the implementation before you postulate the problem. Because what the implementation of consistent hashing ring is, however sophisticated, is just a neat solution to a niche problem. And the real problem statement stems from system design requirements, not from how can you operate bits and bytes and hashes. So I'm going to do my best to arrive at the problem statement from the top down, and then talk a bit about the actual algorithmic tricks, and then dive out to talk about the big picture again. As a system design concept, when I think about presenting, explaining, or giving a talk on consistent hashing, I've distilled it down into two main objectives of this idea. Objective number one is that consistent hashing makes it clear that all the keys, or whatever you have to allocate, shard, distribute across multiple machines, nodes, services, data centers, this allocation is done in a way that if you need to perform reallocations, if you add machines, if some machine dies and other machines have to pick up the load of this machine, or if you increased capacity of one machine and you wanted to rebalance the load to account for this extra capacity, like it's a file system and you added a larger hard drive, you would like to use it. So the biggest conceptual advantage consistent hashing gives you is when reallocation has to happen, it minimizes the reassignment. It makes sure that, mathematically speaking, only what has to move moves. And I'll talk about this in detail pretty soon. And the other huge advantage of consistent hashing is that it allows for what I would call zero orchestration. Again, speaking in system design terms, if you need to distribute some data across multiple machines, you kind of have two options. Option number one, you have some orchestrator, which would break the key space into sections, allocate certain sections to certain machines, orchestrate which machines are faster, slower, are more loaded, less loaded, and whatnot. That's one approach. And the other approach is effectively consistent hashing. When you say, you know what, I do not need the orchestrator. All the nodes can figure out which parts of the key space belong to them by themselves, and the clients can also, the clients or the load balancers, we'll talk about this. The clients can figure out which machine to go to, which node to go to for certain key, because they can also apply the same computation and figure out which node is responsible for certain key. So it's not that we don't need any orchestration. We need some data authority on what I call the state of the fleet. Effectively, the state of the fleet is the list of machines currently serving this data. In practice, it would be a list of machines plus their capacities. So like a map, a dictionary between machine name or ID or IP address to percentage of the load it can handle. So as long as you have some log service, a log file system, where you can store this mapping, where you can store this weighted list of machines, and the service is supposed to be available to all the nodes that store the data and all the clients, or all the load balancers at least. You can use consistent hashing in a way that does not require any extra components that are must-have. You can have them, again, you can have like load balancers to support GET requests or such, but you don't have to. And if you go into advanced topics, what I would recommend is client-side load balancing, but that's a different conversation. So once this approach is being taken, somehow so I will talk about the algorithm eventually. That is important, I think, in my head. Full disclosure, I kind of reinvented consistent hashing when I was younger. I reinvented most of it except the actual ring, except the actual implementation. So then when people told me, hey, good job, now read up about this consistent hashing ring, once I saw the pictures, everything became clear in my head. So maybe I'm biased towards my own understanding of what consistent hashing is about, but I still think the actual mathematics behind the algorithm is of less importance compared to the fundamentals. And the fundamentals is that once you realize it is possible to distribute and redistribute data across multiple machines without orchestrator, so long as all these machines have access to some data authority that tells them which ones of them are up and running and in operation, you can do it. And in addition to these two major properties, which I just covered, even reallocation and no orchestration, there are some nice, useful second-order properties which just follow naturally from the implementation. It doesn't matter if you use the ring or come up with something else. So one is you can always not just map keys to nodes, but you can map keys to ordered list of nodes, primary, secondary, etc., which comes in extremely handy when you're building like a distributed file system. So if you have 1,000 machines and you want some chunk of data to be stored on 10 machines, consistent hashing allows you to pick those 10 machines, not just one. So that if one of them dies, the fleet would automatically figure out, oh, this chunk used to have a replication factor of 10, now it's only 9. So here's the 10th machine, I know it automatically. And here are the 9 machines that can take this data, from which this machine can take this data and copy it to itself and maintain this replication factor of 10. That's a huge thing. Weights assignment comes really naturally with the ring-based implementation. And last but not least, if you would like to know the history of where some keys used to live, for example, if it's like a cross data center database replication, which was my case in a distant past, you may want to hold on responding to certain queries, to certain keys, if you have enough reasons to believe the database might be behind in your data center compared to the place where this data was supposed to come from. So you could just say, you know what, if the reassignment took place and the replication delay between these two data centers is 5 seconds, I'm not going to serve the data that used to be there for the next 5 seconds. I need to make sure the database has enough time to catch up. That's a very simplistic view. It's just, my message is that it's possible to figure out which data was where in the past. The algorithmic trick, again, I will talk about the ring, and I will not talk about the implementation much, even though if there's enough interest, we could probably talk about this in detail in some other time. I just feel like it's implementation, it's coding, it's DSA, data structure algorithms. It's not really system design. So let me try to illustrate by example what do people mean when we say minimize reallocation. Say you have 5 nodes, A, B, C, D, and E. If you know nothing about system design, if you're an engineer and you're told, hey, we have this single database, single machine that stores the data, and it doesn't have enough capacity. Maybe it's not enough CPU, maybe it's not enough disk or RAM. So please shard it across 5 machines. We just computed 5 is enough, and we bought those 5 machines. Here they go to you, A, B, C, D, E. how would you distribute the keys across machines? Well, the trivial solution, which is absolutely correct, is to say I take the keys, I hash them. Sometimes you don't need to hash the keys if they already are hashed for you. Sometimes they are evenly distributed, but in practice, you never go wrong by saying I'm going to hash them. You take this hash as a number, modulo 5, get a number from 0 to 4, and these 5 numbers, 0, 1, 2, 3, 4, map to 5 machines, A, B, C, D, E. Wonderful, amazing, fantastic, it works. What's the issue with this? Reallocation. If suddenly, well, if you know you have reserves, if you know you have extra capacity, and one machine goes down, which is expected and normal, or maybe you just decommission it, you need to recompute the assignment. If you just change this hash modulo 5 into hash modulo 4, then all the assignment just changes dramatically. So it's not that there's some locality with respect to which machines used to serve which parts of the key space or which keys. It would just the hell's going to break loose. Or you could say, you know what, I'm just going to say that everything that, let's say if machine B has died, I'm going to say, well, everything from B goes to C. Well, in this case, you have A, D, and E operating at 100% capacity, and C is at 200% capacity. Even if you can handle that, that's certainly not a recommended way of doing things. I'm going to explain how to solve this problem correctly, like top to bottom. First, we're going to figure out what exactly is minimize and reassignment. Then we're going to figure out how do we come up with more than one node per key. So not just this key goes to this node, but an ordered list of primary, secondary, all the way to the last in priority. Then we talk about weights and naturally get to the topic of virtual nodes, which I think is a bad term, and I'll talk about that. Imagine you have a few nodes, like in our case, 5 nodes, A, B, C, D, and E. And there are no weights, as in they are all identical weight. For the simplest explanation, let's assume there's 100. There are 100 keys. With 5 nodes, every node gets 20 keys. It's all approximate. It's never going to be perfect. But in practice, of course, we're not going to talk about 100 keys. We're going to talk about 100,000 keys. And the approximate divisions would be about approximately correct. So 100k divided by 5 is approximately 20k, give or take some small number. We'll talk about hotkeys later. Hotkeys as in 2 popular keys that are screwing up your distributions. That's towards the end. So just keep in mind that when I say 100, I don't mean the whole database is 100. The logic holds for any number. It's a good number to pick for scaling purposes. By the way, since I've given this talk a number of times, I can guarantee you it's the best number, because 100 and 5 versus 4 versus 5 machines gives you nice round numbers when you divide them. It's a lot better than 6 or 7. Trust me, I've tried that. So if you have 100 keys and you have 5 machines, you would imagine each machine owns 20 keys. We're talking one-to-one assignment for now, forget secondary, ternary, etc. Now, if one machine goes down, you have 4 nodes left. So each of them should be home to 25 keys. The minimized reassignment solution would look like this. Each node retains its 20 keys. Whichever was assigned to this node prior to one of the 5 nodes going down is still belonging to this node. And the node that died has 20 keys to be reshuffled. So ideally, these 20 keys are reshuffled across the remaining 4 nodes, 5 keys per node. That's simple. And again, if we go from 4 nodes to 5, what you would imagine should happen is each of the 4 nodes had 25 keys. Once the 5th node is added, each of the node keeps 20 keys. Doesn't really matter which ones for now. But out of 25 keys that used to be in node A, if you add node B that was dead before, out of 25 keys node A had, 20 would remain, and node A would give away 5 keys to node node B that is currently emerging. The important part is adding a new node, let's say node B, should never reassign keys between, let's say, D and E. Should never ever happen, which is exactly the issue with like hash modulo based approach. Okay, this was verbose, but hopefully clear enough. Now, the simple, I would say mathematical way, although I think the proper term would be the simple computer science way. The simple combinatorial way to reason about this would be, or could be, the following. Imagine, again, it's not the algorithm, not the solution, not the idea, just the easiest possible explanation I can think of. Imagine we have 5 nodes max, and we only care about one node going down, for the sake of simplicity. What you could do is you could come up with a list of ordered pairs of 2 nodes, primary and secondary. So AA, AB, AC, AD, AE, BA, BC, BD, BE. There's going to be 20 of those. It's A, 20, A. No, wait. It's unordered 5 choose 2. A from 5 to 2, which is 5 times 4. 5 times 5 minus 1. So it's going to be 20 of those, which is a nice number that divides 100 and results in 5. So if you have this list of 20 possible ordered selections of 2 nodes of 5 from from AB at the beginning to like ED at the end, it's 5. It's 20 elements total, and if you take the hash of the key modulo 20, the standard pure modulo, no tricks, you select the element at this index of this list, you would know that this key is assigned to certain primary node and certain secondary node, or certain backup node. So now imagine that the logic is as follows. Since we do have this log file system, log service, which tells us which machines are currently up and running, the client needs to look up certain key. The client applies this function, computes the hash, takes modulo 20, and knows that the primary is B and the secondary is, let's say, C. If B is up and running, the client goes to B. If B is down, the client goes to C. That's the logic. That's it. Because look, if all 5 nodes used to be up and running, clearly you have this even 20% each distribution. Now when, again, for our example, if node B dies, whatever used to not have B as the primary machine stays there. Whatever used to have B as the primary machine would need to be reassigned. But we already know that by design, as the way we constructed this assignment rules, there would be exactly 5 machines that have primary B, secondary A. Exactly five keys. 5 keys primary B, secondary A. 5 keys primary B, secondary C. 5 keys primary B, secondary D. 5 keys primary B, secondary E. So that's exactly the design we need. Of 20 keys that used to be assigned to B and are now reassigned, they would go 5 each to 4 remaining nodes. That's it. Again, this is not the solution that I recommend implementing. Although if you have a really tightly constrained system, like 5 nodes max, their names don't change, and you only need to support the situation where at most one node fails. Under these tight constraints, when you know they're not going to change, you can just implement this simple hash function and be very happy that you've done this job in half an hour. For our purposes, with respect to consistent hashing, that's just the illustration, just the explanation. Now, let's try to add weights. As we briefly covered before, imagine you would like some node, let's say D, to take twice the load. Well, you can just say I'm going to have D1 and D2. They appear twice in my lists, in my assignment rules, but ultimately they all go to the same machine D, to the same node D, which makes me look at the system which effectively has D loaded twice as much as any of the other machines, any of the other nodes. If your system requirement is something like make it possible to increase D's allocation by 10%, so from 100% to 110%, then mathematically the only solution you can think of is split every single node into 10 beforehand. So like A1 to A10, B1 to B10, C1 to C10, etc. And then add D11 in addition to D1 to D10. Which, in a way, it's a good idea. It's just for our simple toy implementation of picking primary and secondary nodes, this would just blow up the solution. The combinatorial space would become huge. So we already had to do order n squared elements in this sorted list of pairs. If you have 10 virtual points for each machine, you need to select at least 11, right? Because all the first 10 could belong to the same node, so your secondary is never there. And 50 choose 11 would be a huge number. Also times 5 times 11 factorial, it would be a huge number, so it's implausible. You could come up with the idea to compute hash modulo this number algorithmically. It's not hard, like iteratively compute hash after hash after hash, take the right modules. It's just absolutely implausible. And you would need to do it for every single key, for every single machine. Super slow, super ineffective. So the point of this slide is to introduce this idea of weighting by making some nodes split into multiple nodes artificially. There's a huge disclaimer to be made here. Sorry in advance for the fine print, but it's really important. I'll describe it in my own words. The slide is here for your reference. So when I talk consistent hashing, more and more frequently these days, the term virtual node comes up. So people read some online tutorials, and they refer to so when you have a node, in our case D, and you want to increase its load, increase its fraction, its share, people talk about increasing the number of virtual nodes assigned to D. What they really mean by this, correctly, is the number of segments, like short, tiny segments, on this consistent hashing ring. So it's mathematically sound. But I insist that the term virtual node is extremely misleading, because you're going to have a bunch of small nodes, a bunch of small sectors of this ring that all, by definition, are served, are managed by a single physical node, be it a virtual machine or a physical machine. So it's really, when you use the term virtual node conceptually and you start thinking from the consistent hashing ring as opposed to the top-down system design solution, it's really easy to get confused by assuming that every single small, if this is your ring, you have the smallish parts here and there, and you start thinking that this small part is supposed to be my sub-node, virtual node. Nobody even knows what's the right number of virtual nodes per real node. I've experimented. It has to be at least 5K, ideally more than 10K, to give you decent precision in terms of percentages load. So it's just a confusing term. What I recommend doing instead is all this is about sharding, slicing the key space, the hash key space. This ring, which we'll talk about eventually, has to do with the key space, with the hash key space. And again, I also sometimes see tutorials which say, oh, imagine you have a really huge key space, like 2 power 100 something. First of all, it doesn't matter. It really doesn't. As long as you have enough data points on this key space to cover all your needs. You can use 2 power 32, 2 power 40, 2 power 100. As long as 2 power 32 is 4 billion. As long as you don't need to put more than a few million data points onto this ring, the effects of discreteness or even collisions will be negligible. So just don't worry about this. My mental trick is, when you're thinking about sharding a key space, think of the hash as a continuous function. So forget bits, forget discrete mathematics. Think of it as a Platonian ideal of a continuous number of arbitrary precision. It's perfectly precise. It doesn't have any resolution. It's a point on the continuous line. In this case, it would be a continuous ring. So it has an infinitely small dimensionality. It's just a point. And then eventually you would need to split this range into sectors, into slices. Well, first of all, you would hardly have collisions. For any reasonable modulo, you would hardly have collisions. Second, when you do have collisions, it doesn't matter in which direction do you resolve those, even if you do it wrong. As long as you do it consistently, you would be perfectly fine. The mathematically correct solution would be to say, you know what, I'm going to go look for the number that is the first number not smaller than my number on that begins this interval on the ring. Others would say, well, it's equal doesn't count. You should take one step ahead and then look for the same number. Others would say if it's equal, I take the node with the smaller number in the nodes list. In theory, all this results in different solutions. In practice, the differences are so minor that chances are you would never ever notice them in your life. So it's just not important. Ignore this part. Just view this hash space as a continuous function. You can mathematically think of it from being from 0 to 2 pi, or closed on 0, open on 2 pi. That's it. It's like a ringy thing. Or you can think of it as a 0 to 1, 0 inclusive, 1 exclusive. It really doesn't matter. And then, so much like with some other clever tricks, this very idea of consistent hashing kind of relies on the fact that you can map things of different nature into the same key space, into the same hash space, and then look at their interconnection, look at their relationship. All we would be doing eventually is mapping both the machines and the keys to the same hash space, and that's it. So just keep in mind that every single data point, every single point you put into this hash space, be it a line or a ring or whatnot, has infinitely small size. It's of 0 length, 0 thickness, 0 thickness, and all you care about is I'm going to color some ranges of this ring in certain colors, and I need to be able to answer the question: to the segment of which color does certain point fall? That's it. So I will carefully use the term virtual node, quote unquote, when I describe things in the next couple of minutes, but I really encourage you to not use this term because I think it's broken. Okay, talking the algorithm. The ring itself is just a specialized probabilistic data structure. All it does is effectively, as I described before, it maps the key into a permutation of nodes. Permutation as in, if you have 5 nodes, A, B, C, D, and E, all this function does is, given the input key or its hash, it gives you the sorted list of A, B, C, D, and E. Technically, mathematically speaking, well, more like speaking in computer science terms, the function itself would take 2 arguments. It would take the key from the key space hash, or unhashed key, which you can hash yourself, and the state of the fleet, which we covered before, is stored in some central authority, most likely log file system. It could be Zookeeper, could be console, could be etcd, whatever you prefer. So mathematically speaking, the consistent hashing ring is a function that takes state of the fleet, list of machines and their weights, the key to shard, and it returns you the sorted list of which nodes to go to. That's what it does from the computer science perspective. Of course, in practice, you hardly ever need this whole complete picture. In practice, there are 2 differences. One difference is you never ever need the complete list. If you have 1,000 nodes, you don't care about a sorted list of 1,000 nodes. You care about the first few, first 10 maybe, oftentimes first 1 actually. You could say, hey, request top 3, sometimes top 20. You don't care what is in the position 100 there. Because if it's like a distributed file system and you want to store some shards, some chunks of data on multiple machines, well, you can hardly imagine the chunk that is a replication factor of more than 100. It's more than enough in practice. So you just have this method to generate top n. You can think of it as a parameter to this function, how many to return. You can think of it as a generator, which gives you which you can use to get the first top choice, and then iterate further would give you the next until you're done with the last one. Doesn't matter. The second practical difference is, since it's a data structure optimized for performance in the real life, you wouldn't compute it all the time with this state of the fleet plus the key. What would happen is it's going to be like a singleton. In fact, it's going to be a singleton. I was thinking a thread local singleton. It's a singleton. This singleton updates itself once the fleet changes, once the state of the fleet changes. So the piece of logic, the piece of software that has to know where to go to in terms of the consistent hashing assignment of keys to nodes, this module, this machine, this code will be subscribed to the updates to the state of the fleet from the authority you trust. So the data central authority that stores the list of machines currently active, potentially with their weights, has to support two functionalities. It has to support GET requests, given the current state. And you need to be able to subscribe in a PubSub fashion to whichever updates happen to the state of the fleet. It is done this way mostly to save on time and performance in CPU. Because in practice, if it's a high loaded system, state of the fleet changes highly infrequently. Like I would say, there could be weeks and weeks with no changes. Whereas the computations happen potentially thousands of times per second. It could be tens of thousands if it's a huge multi-threaded machine. So the data structure is, forget system design, the data structure, we're talking about the algorithm, is skewed dramatically towards slow recomputation once the fleet state changes, coupled with extremely fast computation of, hey, I have this key, where do I go? Yeah, that's it. Clearly, we don't have the list of the nodes maintained. Otherwise, we'll have to hard code those lists, and it will be painful. So what the proper implementation does, it's agnostic to whichever keys can emerge in that central authority as nodes serving my data set. So it's not just A, B, C, D, and E. They would be like data center machine names or IP addresses or some console names to resolve or whatnot. So there's no condition that all those should be like single digits from single letters from Latin alphabet and stuff like that. So yeah, as I said before, the biggest thing you have to worry about is applying this function extremely fast. Once you know the state of the fleet for the next millions and billions of applications of queries. Mathematically speaking, this is really easy to solve. And here's the wrong solution. It is correct, but it's just too slow in practice. You take the key, the key that you need to find which node the key for which you're looking for the node that's responsible for this key. You take this key, you concatenate this key with every single node name, and you compute some hash of this concatenated thingies. So if nodes are like A, B, C, D, E, and key is 42, you compute any hash, MD5, CRC2, CRC32, share, not recommended, but you could, too slow. You compute those hashes of the combined key plus machine name, and you sort the list of machines by these hashes, because hashes are comparable, be those numbers or strings. And you pick the top machine from this list, which is currently available, and it has the minimum or maximum hash, however you sort it. That's your solution. If you need virtual nodes, if you need different weights, then you would need to do it not just once per machine, but however your denominator is, however large your denominator is. So like if we take the denominator of 10 as before, so A, B, C, E were 10, and D was 11. You would have 51 total, and you would have to compute 51 hashes just to find the maximum one. You cannot save and compute on any hash because it could be the maximum one. But you would need to compute all of those, throw away everything once you know what the maximum one is. Extremely ineffective, especially if you need to do it on older machines or on more than one machine. But mathematically, it's going to solve the problem. The data structure we have for the ring is pretty much doing the same computation, but in a highly more effective way. All it does is, we'll get into the ring finally. All it does is, for each node, you compute a bunch of hashes for this node. I like to think of those as pseudo random numbers, with the node ID and node name being the seed. That's one way to look at it. You can look at it in any other way. You just need to have some deterministic approach that would take the node name as the only input and give you a bunch of numbers, a bunch of hash numbers from a certain hash space. As I said before, you can mathematically treat the hash space as a continuous function, so that it's arbitrary precise number between 0 and 2 pi or whatnot. In practice, of course, it would be like from 0 to power 64 minus 1, or from 0 to power 32 minus 1. The number of points you would take per node would be proportional to the number of virtual nodes, even though I hate this term, allocated to this machine, to this node. Just Keep in mind that since the data structure is probabilistic, it would not be as precise as these modular permutations. So you would need to have a lot more points. Don't use just 1 or 2 points. I did the research, I did the math myself many years ago. If you want your, you can do it yourself, it's not hard. You can just experiment numerically. But fundamentally, if you want your load percentages to be within like 1 or 2% off, you need at least 5,000 data points, 5,000 virtual nodes per physical node, which is a huge number for most of us. I mean, it's small for computers, but it looks like a big number, which is exactly why I think the term virtual node is so misleading, so imprecise. So you take this hash space, you make this linear hash space into a ring. So you just assume that it wraps as you keep incrementing, as you keep going like in a positive direction, you go further and further, but then if you go past the maximum, you wrap around and go back to 0 where you started. That's the ring. And then, yeah, you compute a certain number of points per node. The number of points is proportional to the weight of this node. So yeah, I think in my experience, I had like 5K as a baseline number. So the node with like 0.8 weight would get 4K, 4,000 points. The node with twice the weight would get 10,000 points. You compute these points in a pseudorandom fashion. Pseudorandom means whoever wants to use your service would compute the same pseudorandom numbers. And you toss those points onto this ring. You then build a data structure which allows you to quickly answer the following question. For a given location on the ring, what's the nearest point clockwise? Or rather counterclockwise, but it's actually immaterial. What's the nearest point counterclockwise? Well, this problem is identical to doing the opposite transformation first. You first throw out those points, and then each point is assigned a color, where the color is uniquely described by the machine, by the node index. So colors can be A, B, C, D, and E. And then you just, all these points keep going clockwise until they hit the next point, or potentially going around, wrapping around 0. So your hash space, your ring becomes colored. And then in order to answer the question, to which node should certain key belong, all you need to do is you compute the hash of this key, and you look at the color of the point at the respective point on this now colored ring. That's actually it. That's all the magic. I made some pictures myself. They were not as sexy as I wanted them to be. So I spent a few minutes and found some online tutorial, which I'm going to link to, and took the pictures from there. So this is the really simple tutorial picture. Keep in mind, in practice, it would never be as clean, because in this example, you literally have a single point for A, single point for B, and single point for C. And as you can see, B, the blue section, is much shorter than A, the red section. That's the imbalance you get by using too few points. In practice, you would have, again, thousands of points for A and B. But the thing is, once you add the new machine, the picture kind of changes, and this D gets some fraction of this ring. In practice, these are the virtual nodes. In practice, you would have multiple segments of the same color, and that's all you need to be able to imagine. Just keep in mind, in practice, if you were to color this for a production system, it would not be as clean. It would be a bunch of random colorful noise, because the number of segments per node would be remarkably huge. But if you zoom in, like in the Mandelbrot set, you would actually see those segments like you see them here. Now, it should be pretty clear to see that, for example, in this picture, in the picture we're looking at right now, if the red section is removed, you just keep coloring whatever is before it. You just imagine red is gone. So what used to be red is now black. And black has to be colored by the color that precedes it counterclockwise. So in this case, orange would take over the red from 12 o'clock to 2 o'clock, and the red at about 5 o'clock. That's what's going to happen. So in this particular example, it's pretty bad, since after red is gone, it's orange taken over. But again, if you have a lot more sections, it's guaranteed to be mathematically even in terms of the evenness and minimized allocations we just described before. So yeah, if the color disappears, the other color takes over, and that's pretty much it. Final note on how to implement this. I'm assuming most of the people who are studying computer science and got into system design, if you ask them how to solve this problem of figuring out what the color of the point is, what the color of certain part of the ring is, and they would say, oh, I have like in the order of tens of thousands data points. I need to figure out the nearest data point counterclockwise. So I'm going to go with interval tree, which is a correct solution algorithmically, computer science-wise. It would be logarithmic in the number of points, which means if you change 10k points to 100k points, it's just a constant time penalty because it's logarithmic. But since this solution is solved under very specific circumstances, specifically very few updates, very infrequent updates, very infrequent ring rebuilding, and a lot of reads, thousands per second, if not more. The real-life optimization is, in fact, to not use a single interval tree, but to allocate some memory, hundreds of megabytes probably, to break this key space, this hash space into fixed size intervals. That's just the simplest idea, but it works. You can come up with a better idea if you want. You just break it into fixed size intervals, and within each interval, you build a small interval tree of whatever belongs to this even part of the ring. In many cases, if you allocate enough memory, you can find the trade-off yourself. But if you allocate enough memory, in most those buckets, you would have a single color. So it's order of one lookup. And if it's not order of one, there would just be 2 or 3 colors within this interval. So 2 or 3 lookups over a segment tree are optimized away into just a few if statements. So it's effectively becoming order of one per lookup. There are other ways to do it. Let's not spend time doing it. It's just keep in mind this works. In practice, if you want to be able to also find the secondary, ternary, etc., you would need to optimize the data structure somewhat, like pre-compute a bit more, so that for every single data point you can pre-cache first, second, third, or have some iterator that goes clockwise, skipping the same colors you have already seen. Entirely possible, not too expensive. And I mean, keep in mind, the whole premise is that the ring is recomputed once a week, or if not less frequently, and the queries are done thousands of times per second. So if this recomputation takes 10 seconds, it's no big deal, because what you're optimizing for is the actual performance of the system when it's stable, not when it's reconfiguring. So tons of clever algorithmic ideas are in order here. All right. I don't think I will talk more about the algorithm. So if there are questions about that, let's talk about them now. None? Real good. So back to system design. Covering a couple topics in the order of increased complexity. By the way, it's probably going to be one of the shortest and dense educational episodes, which I think is awesome. So covering a couple topics in the order of increasing complexity. One huge advantage, which I started from, is that this solution does not need an orchestrator. In practice, so once again, as I said before, there's no constraint for you to not have the orchestrator. You can have a load balancing cluster. You can have a bunch of machines that listen to the same zookeeper or whatnot console. State of the fleet pops up, and the only job of these nodes would be to maintain these rings in memory and to be able to serve requests such as, hey, for this key, where do I go? At a huge QPS rate. These load balancers will be totally independent from each other, much like all the nodes and all the clients. All they need to have is access to this orchestrator, or access to this log file system, the log service, where the data authority information about which machines are currently up and running, which nodes are currently up and running with their respective weights. This information, this map, should be delivered and updated real time on these load balancer nodes. In practice, what would happen is when the client would like to retrieve certain key, I would recommend that the node itself that receives the request to also confirm that this key does indeed belong to this node, just in case there's a stale request. It's highly unlikely, and it's probably okay if it's not the case, but I would still make sure that this node double checks that the routing is indeed correct. This node does indeed possess the part of the ring to which this key belongs. So it needs to confirm that the color of the key matches the color of this node, so to speak. So then you can have different designs. Maybe if the color does not match, this node could automatically go to another node. It doesn't have to, but it could, so that the user is happy. Maybe it could return to the load balancer. Hey, I'm not the right node. Please use the load balancer. Reissue the request. So the user doesn't see any changes. The user just gets the data. But if you so happen to be in the middle of the change, the user would just get the same response but slower. Or what I would of course do is I would try to introduce this routing logic on the client side library. So there's no need in any load balancers. The client itself talks to my nodes through my own library that is linked into the client, and this part that is linked into the client is subscribed to the updates on the change of the fleet. So the client behind the scenes, the user code, the client, knows exactly which node to go to automatically. Yeah, that's the part about the orchestrator. Another thing, I also briefly mentioned this. What if your reassignment takes time? So there's reassignment in the mathematical sense of this word, and there's reassignment in the pragmatic, practical, technical sense. There's reassignment that the data has reached my machine, my node, and is available there. For example, if it's a cross-data center data replication from a database, you may know for a fact that between these two data centers, there's delay in replication, let's say 5 seconds. In which case, it might be the case that technically, since that data center is now out of rotation in my data authority, my data center currently owns that key from the standpoint of consistent hashing, but the data is not here yet. If you don't do anything, you may return inconsistent data to the user because they used to go to the primary data center of this database, and now they go to the replica, which is behind. But in practice, since it's consistent hashing, you can always say, you know what, I'm going to look at the history of where did this key belong in the past, let's say, 10 seconds. If it used to belong to a data center from which I may be under-replicated, then I'm going to just wait 5 seconds, return 500, return later, or whatnot. All these are fine options. So yeah, that's actually the beauty of this architectural idea, that you don't have the orchestrator, but you have the data authority with respect to configuration, which is in a log file system like Raft or Paxos, and you can always replay it, and you know exactly what was supposed to happen in your fleet, in your system. The canonical example of consistent hashing, I think one of two canonical examples, is a distributed file system. That's something I often ask candidates on interviews when they say they like to design things, but they've never done it from scratch on a grand scheme of things. I'm like, awesome. Ask them two things: design a torrent protocol, how to copy the same file to 1,000 machines in a data center, and design a distributed file system. Distributed file system is pretty much a canonical example of using consistent hashing at scale. All you need to do is, once you break the file into chunks, you need to figure out to which node does a certain chunk go. You would have some replication factor, so you would have some magic number associated with each file, or with or the default factor. So it could be like 7 or 10, 20, which means each chunk should live on at least these many machines. And the allocation between chunks and machines is exactly the ring-based consistent hashing approach. So once machines are down, or machines are being added, or you add hard drives and you would like to use those, you just change this data authority, and it populates everything, and the data is magically reshuffled. It is, of course, slightly harder than this. You need to figure out which machines to send the data, which machines receive the data, how do they know which files to send and receive. But once you know that you can use consistent hashing to always compute the proper allocation between chunks and nodes, you're good to go. By the way, yeah.
So I have a question about node dying and other nodes learning about it. If there is a central authority to which heartbeats from all the nodes is being sent periodically, then it is easy for the central authority to know that when a certain node goes down. But if there is no central authority, like in the previous slide or two slides before, there was a situation wherein we could have done this without any central authority, orchestrator, if you will. How will the other nodes learn about this? Like, is everyone like subscribed to heartbeats of all the other nodes, or are they using gossip protocol or like something like that?
Excellent.
And how soon will they come to know about it?
Excellent question. I'm gonna cheat here. So here's the cheat answer. So first of all, if you can design a system so that nodes don't talk to one another, for a large number of nodes, it's always better. Because for 10K nodes, it's just too many connections. So on the one hand, yes, I'm claiming there's no central authority. On the other hand, you're right. That somebody has to receive those keep alive and pings and stuff like that. I'm going to cheat by stating the following. The design I'm suggesting assumes the data center, or a bunch of data centers, which already have the central authority, as in the leader-elected Raft or Paxos cluster, like Zookeeper, and the keep alive mechanism in place, which technically is the case for most production data centers. Because, like, think about it. If every single system you build would have its own keep alive engine and its own leader that would receive those keep alives, and its own leader-elected clusters of a few machines to receive keep alives, so that if one of them goes down, the others would still receive keep alives, it's just a pain. So for a real production system, if you are in an existing cloud, like Google, Amazon, Microsoft, Oracle, I'm gonna assume there exists such a system, which is A, leader-elected storage, such as Zookeeper, and B, it performs the keep alive validation and it knows which machines are down. So there already is some kind of a pub-sub to which the events of machine down, machine back in back in operation is being published.
So in that case, so if we have this pub-sub mechanism, uh, suppose if the system requires us to guarantee like 5 nines, so can we really build such a system such that using the pub-sub and like will there be any changes in the system design to guarantee this high availability requirement?
Well, the art of system design is to find the right trade-offs. If you need 5 nines, chances are you are going to use a data center that provides these 5 nines, the cloud provider that provides these 5 nines. If your requested 5 nines on bare metal, we're in the territory of designing data centers. Power supply, secondary racks, extra network cables, custom hardware to perform packet switching on the fly just in case. I'm not an expert here. I just know it's hard but possible. In fact, it's highly profitable because it's one of those few things left on this planet where it's hardware, not software, but it scales as if it's software. So, I mean, I know confidential stories about like boxes sizes of the fridges, which is like a 1,000-port switch that is hardware connecting things here and there just to maximize the throughput, maintaining latency at far below 1 millisecond. Those things exist, they're real, and they're totally paying for themselves. But if you are to design such a system, well, chances are you're given enough resources, budget, and talented people to make things happen. If you're using the cloud, such as Amazon, and you need 5 nines, the true question from a system design perspective should be the following. Do I need to build my own consistently hashed data structure, data flow? Because in your case, DynamoDB is going to use consistent hashing implemented by Amazon. Even if you believe you are better than Amazon developers, which may be the case, but still, their systems are highly more tested. Their systems can rely on the internal infrastructure details that you don't have access to, and they know intimately. and if some issues can potentially happen on their side, like with hardware or with their network cards or their cooling, they would know it far before you, and it's their job to keep data center and the basic Amazon services at a certain number of nines. So if you really care about the number of nines in your consistently hashed system in your design, my number one recommendation would be look for the primitives that are guaranteed by the external provider, such as AWS in this case, that give these guarantees. You'll be surprised. Well, so first of all, 5 nines, it looks huge, but it's actually quite some downtime. I mean, 5 nines is 0.1 seconds per day, right? So it's more than half a minute a year.
I think it's about 5 minutes, right? I know, but it's in that range.
I did the math in my head. 84k seconds, approximately 100k seconds in a day. 100k is 10 power 5, so 10 power 6 is 10 times more. So anyways, it's by far not zero. It's not negligible. And you'll be surprised what actually causes downtimes of this frequency. It's oftentimes it's something as simple as, oh, I have this alarm and alert here and there when my disk is full, but somehow it didn't fire properly. So even though it sounds like it's 5 nines, so it's remarkably effective, the actual outages would be most likely caused by human errors. And you don't want to be the person blamed for not setting up the page and alerts correctly. You really, really want to outsource it to a larger entity that is doing this for a living and has learned from their mistakes for dozens of years.
True.
I mean, it's not that hard to build a database. It's not that hard to build something that can fail over something fails. It's really hard to maintain it at scale with all the human factors taken care of. So I don't recommend that.
Okay. One last question with regards to the consensus. So between Raft and Paxos, which one is more effective in time efficient? And in the case of a distributed file system, what should be used?
Well, again, advice number one: don't do it yourself. That's one of the things I would not recommend implementing. Advice number two: if you want to use something existing, don't choose based on the algorithm. Choose based on industry practices. So if you're in the cloud and you need to have high guarantees, use something this cloud provides. If you use AWS, you can use DynamoDB, and you don't have to worry about which algorithm they use internally. If you have to potentially maintain it, my understanding is that Paxos is impossible to understand. I tried. Raft is kind of understandable. So if you need to understand it yourself and be able to explain it, I would recommend Raft. But there is literally zero chance on this planet that you would have to troubleshoot an issue with broken literal elections in production during downtime, unless you're in a very specific environment. So it's important to stress that mathematically speaking, computer science is speaking, literal elections is unsolvable in the precise meaning of the word solve. The solution is always probabilistic. So you can, for each of these guys, you can come up with a scenario where they won't fail. They're proven to be correct by semi-automatic proof techniques. But you can come up with a weird issue of failures where the tri-state, the limbo state with no leader and thus no updates, would last for any amount of time. It's mathematically impossible. It's just the trade-off is that for this to happen, it is so unlikely and so hard to orchestrate by a malicious entity that you just assume it works. And if you're in this space, you're in the wrong meetup, because I'm no expert. But I don't think there are more than 10 people on this planet who think about this on a daily basis.
Then even I should not think about it.
It's like there's a famous problem that you have a fair coin, 50-50 heads tails. Come up with an algorithm that generates a random number between 1 and 3, so 1, 2, or 3. with equal distribution between 1, 2, and 3. So there are tons of solutions, but the truth is it's impossible to have a solution that is giving you a perfectly equal 1/3 probability A, B, or C in a finite number of throws. Because if you have any finite number of throws, your denominator will be power of 2. And power of 2 does not divide 3, is not divisible by 3. So same with leader elections. It's always possible for something really bad to happen and your leaders would be unelected for a while. But much like with this coin tossing, it's mathematically impossible to have a solution that is guaranteed to converge in a fixed number of steps. But for any number of 9s, add a few extra tosses, and you're good. Yeah, I hope it was worth it. All right, where were we? Yeah, so not talking about file system. It's kind of covered many times. Thanks to Maxim, by the way. Thanks for pointing out that I should talk about updates, not reads. So consistently hashed solutions are notoriously good for high read-to-write ratio systems. If you need a strongly consistent data store with like 1-to-1 read-to-write, so you need to update some keys as frequently as you get those, and you need to guarantee consistency, it's a whole different problem. It's a totally different conversation. And consistent hashing per se will not necessarily help you. I thought a lot how to best describe this in this session on the Meetup, because it's really an advanced topic. But I think it would be sufficient for all of us to know that the vast majority of systems that have to be reliable, so that if your system cannot lose data, if your number one requirement is you don't lose data, if a machine dies, if a data center is on fire, if my hard drive explodes, I don't lose data. As long as those are my requirements, most systems that support updates would support updates on top of systems that are immutable. So the way it would work internally behind the scenes is you have some read-only storage. You have some updates that are applied on top of this read-only storage. And then every couple of seconds or minutes or hours, there's a compaction phase where they wipe the old data and replace it by a new data and atomically flip some pointer that, hey, this is a live replica right now. So if you're trying to think about, oh, how do I update my chunk of data in a consistently hashed file system, chances are you're doing it wrong. You don't need to update the existing chunk. What you would need to do is upload a new chunk, make sure it's replicated to a number of places, then atomically update some metadata, which may well be stored in a SQL table to keep things simple, and then have some garbage collector to remove the chunks that are now orphaned, so that no file is pointing at those chunks. That's how we would do it in practice. So yeah, I need to point out that consistent hashing is really helpful if it's data access. It's really helpful when it's read-only access. If it's not about disk, not about disk or RAM, so stored data, but about compute, so you need to distribute the workload across machines, then assume all the jobs are somewhat independent, because if you need to maintain the state and guarantee synchronous all penetrating updates, that is a different problem altogether that technically has very little to do with consistent hashing per se. So yeah, basically the verdict here is, think of consistent hashing if you do need this minimal reallocation property once your state of the fleet changes and the weights are changing or the machine set is changing. That's where consistent hashing applies so well. If you put in a huge key value store with consistency requirements, consistent hashing may or may not be the best trick in your bag. I don't think I have a short answer to this. I just think it's really important to mention that if you're thinking how to update consistently hashed file system with a replication factor of 20, you're doing something wrong, most likely, unless either you know what you're doing exactly or you're doing something very likely bad. Yeah. File system is one example. Disk, of course, is one of the resources that is easy to reason about. You can be out of disk. in practice, I think it should be noted that disks are no longer the bottleneck in our systems. So more often than disk, you would need to handle RAM correctly, which again is a good example of consistent hashing application. And compute, as in CPU sharding, is a whole different conversation. So I think in practice these days, where consistent hashing is used more frequently is not the way to utilize RAM or disk carefully. It's to push code to data so that some queries are run next to where the data is. So, for example, take DynamoDB. You have a columnar database, so some data point has multiple fields within it. Could be a JSON object, could be a columnar database with predetermined columns. If you want to filter certain keys and then only return some aggregate on the key for the keys that pass this filter, consistent hashing is not used to distribute the keys these days. Well, in this case, it's used to distribute the computation load of this query. If on your data volume the query should take an hour of CPU time, what you want to happen is for this hour of CPU time to be spread across 3K machines for the query to take 3 seconds or 1 second. And that's where consistent hashing comes into play. That's a big point I wanted to make here. If you advance things, again, so
can you go back to the previous slide? In this case, so the second point, mostly the NoSQL databases, they rely on consistent hashing internally a lot. And you also mentioned that if there are a lot of frequent updates, consistent hashing is probably not our best bet. But the thing is, each of these, like Cassandra and DynamoDB, they all have when they are in their offerings, they all have their consistency levels, wherein like internally, like they have the ability to guarantee like full consistency across all the nodes, or like they have these levels sorted out. So how does it work in that case? How are they able to guarantee consistency?
I don't know for a fact. That's a really good question. But what I think is a true statement is the following. Imagine you're the designer of Dynamo or of Cassandra, and you are tasked with making updates faster, making consistent updates faster. In this subtask of the whole problem space of Cassandra, the fact that the storage data distribution is based on consistent hashing is a given to you. But making sure the update is synchronous, making sure the update is consistent across all the users is the hard problem by itself, and the solution is kind of independent on whether the actual sharding of the data across your machines in a cluster is based on consistent hashing or based on some orchestrator that assigns key spaces from A to B, from B to C, etc. In your case, the real challenge, the real complexity of the problem is orchestrating the distributed update. And whatever sharding scheme is used is something I have to work with. So I think in practice, all these databases will tell you that. I actually have an example further down the slides. All these databases have this. They operate best if it's a huge read-to-write ratio. And one of the most common failure modes, if you use those databases, is if you have a hotkey. The example I used down the slides, since we're talking, is imagine you have some Twitter or Facebook, some social media service, and there's a like button, and people click it. And you would like to maintain the number of likes. And you aggregate those. So there's like likes per post, likes per user, likes per topic or country, and then there's like overall likes. So all the likes go to different application servers of your system, and they go to different posts, and different posts have different keys and databases so that the value is a number of likes. And you just increment those. That's simple. But then you go one level above and you want to compute the number of likes, let's say today, for all the posts on technology. If it's a single database key, it's a bottleneck. If you improvidently think that I'm going to have some top-level key that counts all the likes from today, and every single time something is liked, eventually update multiple keys, including this key, this top-level key would be accessed as frequently by design as all other keys combined, which would kill your database. And that's exactly the failure mode of both Dynamo and Cassandra. You would have the key that is accessed so frequently that this key alone is comparable to everything else combined. Whereas proper NoSQL usage assumes that you can shard things more or less evenly. So in fact, proper NoSQL usage, proper NoSQL data schema and key selection is indistinguishable mathematically from proper consistent hashing key space design. So in which case, if you do the things this way, you have a problem in the design of your usage of the database, not the database itself. And I would argue it's a foolish idea to try to design a database that can handle such load. You can come up with some ideas that, hey, I detect hotkeys and I serve them by dedicated services that are like in memory for these keys specifically. You may want to do it. I just, as a system designer, as a high performance guy, I just don't believe in universal solutions that don't have drawbacks. I would say you better teach your users of your system to design their database schemas and key selection in a way that is friendly with consistent hashing. Was it a good answer, or did I answer the wrong question? Yeah, I mean, it is a good question, and I still recommend this talk by Rick Hooligan, which I posted last time. I think I posted under this video too. He talks specifically about failure modes of Dynamo. How do they... So the humans at Amazon who help optimize Dynamo usage, they have this... Their visual cortex has trained to spot the patterns of bad database design. And this pattern they spot is a hotkey. Because in theory, if all the keys are accessed more or less evenly, adding more machines would automatically lower the load of each machine, which would lower the latency, which would increase your capacity and stuff like that, which is not the case with a hotkey. So if you have hotkeys, please fix it on your application usage level, not on the database level. I do not believe that we're going to see a database in the next couple of years which claims to solve this hotkeys problem, solves it, and takes over the world. I just don't think it's where the point of maximum impact is for modern databases.
How do these big companies they solve it? Like how does Instagram and Facebook, they have so many likes. How do they take care of this? What are they doing?
I can guarantee you they don't have a single database key under which every single increment in likes count by 1 is applied synchronously. Simple solutions that I actually do cover this later in the slides, but simple solutions I can think of right away are the following two. One is you just use different keys. So if you want to compute all the likes worldwide, you just don't use one key for that. You use 1,000 keys. You pick a key pseudo randomly based on the ID of whatever, post, user, or whatnot. And then at query time, if you want to display this total number of likes, you sum those 10K keys. That's one easy solution. The other easy solution is coming from the world of RDBMS, of relational databases, which in the relational databases, transactions are, well, you have to use transactions in order to make mutations, and transactions are expensive. So it's a lot more expensive to run separate transaction compared to making more updates. And the solution that was invented, 40 years ago is batching. So instead of making every single increment by 1 in one transaction, your component that does so can just have its own internal asynchronous thread, which would make like one transaction every 100 milliseconds. So maybe 10 per second, not a million per second. And it would increment this key in the database by however many new likes have been counted here. And well, likes are an easy example because if you lose a few, nothing bad happens. If it's financial data and you need audible logs and paper trails, then you use a bunch of Kafka streams with replayable, fully reproducible sequence IDs, and you can always reconcile those later, which is a huge pain, but it's guaranteed to work. Yeah. Thank you. Yeah, good stuff. You're making me think a lot more carefully about what I say, because the consistent hashing itself is something I know so well, and you're asking harder questions. So that's what keeps me energized, and I think that's what makes our conversation so helpful and fun and useful. So where did we drop off? Latency trade-off. We kind of covered this. If it's about pushing code to data to run the query, you can always increase this replication factor. Replication factor would be a quote-unquote term because it's only replication factor if we're talking about storing the data, like in the file system. If it's a compute cluster, it's not necessarily replicating the data. It's just allowing more machines to take over their responsibility for these computations. But the point is, consistent hashing, as the algorithmic trick, allows you to add more machines. So you pay more money for more machines, but you immediately get decreased latency and higher throughput just because of the nature of how the key to machine assignment works with this ring and sharding. This is something I actually learned the hard way. It's a fairly advanced topic, but I think it's worth mentioning, even though it's presumably an educational episode. So one failure mode people often miss is, what if at some point one of your machines or network links is misbehaving? A good example would be if it's a Windows server and it's started updating in the middle of something. Not impossible. Happened to me. In practice, I think in my case, it was not a Windows update. It was an antivirus. I shouldn't talk about this publicly. So if you design a system that is supposed to be perfectly scalable once you add more machines, it would be foolish to not protect the system against bad apples. So think about it. On the one hand, we know we can always use twice as many machines, and the system will automatically pick it up, reshard the data, and you would have twice as high throughput or maybe substantially lower latency. All good. But that's only if the actual issue is with the data load, but the machines are working perfectly fine and the network is working perfectly fine. Imagine one machine suddenly slowing down. Your system might be screwed if all the clients go to this machine because it's a primary for certain keys. So, and it's embarrassing if in order to speed these things up, you need to have a human that manually, restarts the machine or takes it out of rotation, like decommissions it. So the standard solution to bad apples problem is for the client to talk to more than one machine. So imagine you have five machines responsible, 5 nodes responsible for a certain key, like replication factor of 5. I'm the user. I have the ring. I have the copy of the ring. I have the key to go to. I know exactly which 5 machines have this key. The standard solution would be, I'm going to go to the first of these 5 machines. And then if it fails, I'm going to go to the second, etc., etc. Slightly better solution is the following. First of all, the 4th or 5th of this list could be fresh, as in they may not have the up-to-date data, they are just added in rotation. But the first 3 should all have the data. So I can just pick one of the first 3 at random. That's just an easy way to distribute the load even further. I pick one at random, and let's say I expect the response to come within 5 milliseconds. But I have spikes all the way to 100 milliseconds. I ask this machine, and if no response is back within 5 milliseconds, or 4 milliseconds, or 6 milliseconds, it's debatable, I request the same key from a different machine, from the top 3, at random again. If it fails, I can go to the third machine as well. So even if one machine suddenly is remarkably slow, the users won't notice, because this machine will have tons of pending requests. It would eventually break down under pressure, but it's only going to slow down a couple of requests, a small fraction of requests, to a small fraction of users by those 5-6 milliseconds. That's the way to deal with bad apples. Of course, you would need tons of monitoring and alerting rules so that administrators know, hey, this machine is slow. They will probably first decommission it and then see what happens, analyze the logs, maybe faulty network card, faulty driver. I don't know what could happen there. But the thing is, if you want to design a super highly reliable, fast system, don't just assume your hardware and your software always works fine. You never know what could happen. So yeah, that's the bad apple thinking.
Sometimes I've read this at multiple places wherein they try to ensure consistency. They try to read plus write. They try to keep the number of reads plus the number of writes greater than the number of copies. So they're not reading from just one node at a time. They might read from multiple nodes at a time, and serve like the more like majority data or consistent data. So in this case, how will it work?
Depends on what exactly is your ultimate problem. If you just read the data, then whichever response you get first, you send it further. Let me help me understand the failure.
The requirement is that every node has let's say 5 copies, and when we write data, we write to 3 nodes, and when we read data, we need to read from 3 nodes. Uh, and we are doing this because if we keep the reads plus writes more than the number of copies, uh, then we can guarantee consistency to our customers in most situations.
I think this. I see what you're trying to say. There are a couple things I'm not confused. So one is, if we're talking like military grade or healthcare grade guaranteed data, so you need to make sure the data is exactly what it is. So you could write to 5 places and only return to the user once you have read from at least 3, and they have identical content. That's one sub problem. If you want to be able to update the data once again, then you're in this dreaded consistency cap theorem loophole. You can just, so if your factor is 5, so 5 machines store the data for the same key, you have the node that updates all 5 somehow. Maybe this node dies in the middle. Maybe another node starts updating the same 5, well, for the same key in a different order. You have to worry about all these minor details in all possible failure modes. So in practice, I honestly don't think it happens often when you update the key on these 5 machines, and that's it. What would happen is these 5 machines would have some version ID or version token key of certain record, and it would be upload a new record, then make an atomic flip of the current version of this data, with this atomic flip happening in some other system, for example. So this issue of concurrency between these 5 machines would hardly happen. And if you want to solve it, the solution to this issue is not making sure the data matches on 5 machines. It's introducing another layer of abstraction with atomicity at making the change everywhere at the same time, like two-phase commit style of idea. Yeah, so for bad apples, that's pretty much what what you just asked about. It's if you do want to guarantee consistency. Again, this is not. Yeah, I should have made this comment a while back. So in computer science, sometimes words don't mean what we think they do. Consistent hashing and consistency in the cap theorem are 2 different use cases of the word consistency. And by the way, consistency in databases ACID, atomicity, consistency, isolation, durability. That C, that stands for consistency, is a 3rd meaning of the word consistency. It's like the lay people who just starting with this industry, they would say, "Oh, it's the same word. I've seen it before. I know what it means." It kind of always means the same thing, but in details, all these meanings are substantially different. So it's important to understand that consistent hashing has nothing to do with data consistency with respect to concurrent updates, keeping the data in a consistent, identical, reliable state. That's not the case. So when I'm talking here about serving data that is inconsistent, I'm not talking about data that is inconsistent because the update has partially completed. I'm talking about like hard drive failures or memory corruption, stuff like that. So imagine you do need to serve the data where if one of the machines is misbehaving, you are not allowed to provide wrong results. So like you're a plane in some space shuttle landing, and it's really important for the data to be accurate. In this case, the correct solution, of course, is to say, hey, I have this replication factor of 3. of 5, but I want at least 3 of the nodes to agree on the data, at which point I'm allowed to serve this data, which is fine. But the nice trick to use here is, yes, you do need the data to be identical from 3 places, but waiting for 3 responses could be too slow. So once you got the data from one source, you can start applying the computation further. And then just don't send back the result to the requester, to the user, until you get a confirmation from 2 more nodes that the data is exactly this. Because in the vast majority of cases, the data will be this. So there's no point in waiting those few milliseconds. And it sounds like a small thing, but it kills you at the end of the day. Because those few milliseconds here and there, they add up to huge latency. It's really important to think of asynchronous request processing. Like you would have a state machine in your computation engine, in the application server. You need to carefully design and debug it and test it. But every single time when you say, hey, I need consensus from at least 3 places, I need to wait until I get the same 3 results, that's usually a bad idea. And it's remarkably easy to illustrate with consistent hashing, consistently hashed keys across machines. This is why, as a high-level system designer, I really do not recommend hiding all these details, all this complexity behind a load balancer. So a lot of people would say, I don't care what you have behind the scenes. Could be consistently hashed, could be orchestrator that assigns key ranges. I want a single API endpoint, get data for this key that gives me the data. I don't care how it's working behind the scenes. Well, it's a good idea for simple use cases, but once you're in this distributed transactions territory with guaranteed consistency and guaranteed atomic application or rollbacks, the more logic, the more checks you perform on the data side, the better. So the application server, the application designer, kind of has to know the internals of the data storage. That's why abstracting all this interface down to a single endpoint, single remote procedure call, single RESTful GET request, give me data for this key. At some point, it will backfire. And a lot of times, when big systems fail, or at least when they work correctly but slowly, a lot of times it's because far too many key people who designed it didn't want to think deeply enough, and they just assumed they can just make this GET request and live with it. That's the root of all those latency problems with our modern software. I've seen it first-handedly, inside and outside, so many times. I can't stress this enough. So hotkeys. This TNS, TAAFL is short for there's no such thing as free lunch. There ain't no such thing as free lunch. Again, we're trying to keep this educational, not going deeply into this, and we kind of covered this with that's effectively here, Rahul. That's effectively your question about how to handle this single key that is so frequently updated. And I think, yeah, second and third lines from below are the 2 solutions I recommend it right away. Batch updates and splicing keys into multiple keys and joining them at query time, not at update time. I think that's all we had today.
Can I add just a random thought? We can easily update this to solve another problem. Suppose you have 2 or 3 data centers, and you want to make sure that not only your files are distributed to 10 machines each, but you want to make sure that each data center has like 3 or 4 copies. So you basically it's basically overlap ring. So you calculate different ring for each data center and store them together. I think it would work probably.
It's funny you should say that, because this is actually a follow-up question I ask in an interview when people claim they know consistent hashing. So yes, it's more common across racks, not data centers. You could say, you know what, say it's a single data center, and I want my file system to store a file on at least 10 machines. But these 10 machines should span at least 5 racks. Because racks are behind the same switch, and they are far more likely to fail together if they're in the same rack. So if your 10 machines are like 7 on one rack and 3 on another rack, it's far more likely that you would lose access to this file because 2 rack switches would fail, compared to these 10 machines being on 10 different racks. So the question becomes, use consistent hashing but also give me some extra guarantees on the distribution, not just across machines, but across racks or data center or whatnot. You can solve it, yes. You can solve it with multiple rings. You can have like the hierarchy of rings. So like ring over data centers, and then within each data center, ring over racks, and then ring over files or over machines. That's one solution. You can have a single ring that the logic that makes you traverse this ring clockwise could include skipping. Like if you want no more than 2 machines per rack, you can skip more machines from the same rack and go further clockwise until you have enough machines from different racks. As long as this function is computed deterministically, so all the nodes and all the load balancers and all the client-side libraries can compute it identically, you're good to go. And if you understand this, chances are you understand consistent hashing more than 99% of people. That's at least my understanding, my rough estimate. I am not aware of real-life solutions where they have this hierarchy of rings. I would recommend against it because the list of data centers is small. So keep in mind we had these weights, we had these virtual nodes, and we needed to have the ability to introduce more potentially a huge number of new nodes into your cluster. The number of data centers is almost always fixed, and it hardly changes, and they have fixed names. So I think if you want to use this hierarchical solution on the top level of data centers, you can just use hashes per, like, take the key, concatenate it with data center, or just take the key, XOR it, XOR, exclusive R, with some special number generated deterministically per data center name, pick the maximum one, and go to the data center. That's probably faster if your space of data centers is just 5 or 10. Across racks or machines, you will probably use the ring. But that's total speculation. All right. Shall we call it? Thanks, Fox. Really great speaking with you.